Alright, so we're going to do normal distributions today. Back. I'm going to start on normal distributions today. So, a normal distribution is a particular density curve that is a little black. There we go. I'll put my horizontal axis here. It is that was bad. Low on the ends, peaked in the middle, and flattens out on the ends with an asymptote of y equals 0. It is always above the x-axis. It never touches the x-axis. So that's why I say we have those asymptotes at y equals 0. So this function, called the normal distribution, is always greater than 0. And this function is a density curve. And so the area under this curve the total area under this curve is equal to 1. So in calculus terms, you're going to go from negative infinity to positive infinity is equal to 1. You don't have to put the calculus terms on there. Okay, so this distribution, it actually has a formula, and I always forget it. So I tend to have to look it up. And some people call this distribution a bell curve. It's not really a bell because it's found it. All right. In case you want to know what the equation for this is, and maybe you don't want to, but I'll give it to you anyway. It's 1 over the standard deviation, which we have defined so far, but now I'm going to put this in a different symbol, so maybe I should give you some new symbols here so standard deviation, we're going to write standard deviation for the normal curve and for populations as a lowercase sigma so it's 1 over the square root of the standard deviation of this distribution times this, did I say the square root? 1 over the standard deviation times the square root of 2 pi times that lovely number e that we use a lot to the negative 1/2 times, now we finally get the variable in, x minus the mean of this distribution, which we're going to abbreviate with the Greek letter mu, which is like a U, but it's got a long tail on the left side. So I'm going to subtract the mu. I'm going to divide by the sigma. And then I'm going to take, like I said, do you really want to know what this equation is about? Sure, some of you might. And then square all that. Okay. Are you responsible for knowing that formula? Nah. Yeah. Am I going to ask you to integrate that one? Nah, not even for you post-BC guys am I going to ask you to integrate that one. It's tricky. It looks easy? Okay. Alright. That's kind of what I thought too. It doesn't look real easy. You know, I've done it, but it's not great. Okay. So there are some characteristics of this normal distribution. Display driver has stopped responding and has recovered. Okay. Yay, it does that all the time. So I'm going to draw this distribution several times. Ooh, that one was a little icky, but anyway. This distribution, maybe I should draw it a little better. It's hard to kind of draw it on this board. That's better. All right. The center of the peak, the center of this distribution is at the mean of this distribution, which we're going to call again mu. This curve has inflection points. What is an inflection? You know, like in calculus, what happens at an inflection point? First derivative equals 0. Good. All right. Some of you remember that. So there is an inflection point right about here where you're going down the hill and it's going to kind of cross with you kind of going up the hill. It's a funny little inflection point right there. And if I look at where I am on the x-axis right below that inflection point, that is the value of the mean plus the standard deviation. So it's maybe a little easier to see on a drawing of this distribution that's been drawn well. If you can't pick out that point of inflection, you certainly can just go a little bit to the right and decide that's where the inflection point is. It's always going to be tough to see. Algebraically, it's easier to see when you're looking at the first derivative, but you know, we're not going to look at the first derivative and figure out where that is. So, you know, a lot of times we'll just be given the standard deviation, and we'll work to the inflection point from there. Okay? And, of course, there is an inflection point on the other side of the center, and that value on the x-axis is going to be the mean minus the standard deviation. And I usually end up sectioning off my x-axis with, so that's plus 1 standard deviation. This point would be the mean plus 2 times the standard deviation. And section off another point that would be the mean plus 3 times the standard deviation. And I'll do that going to the left also. So this point on the x-axis will be the mean minus 2 standard deviations. This one will be the mean minus 3 standard deviations. Okay. Now I'm going to do something kind of tricky because there's one more kind of important thing we're going to kind of estimate for today. Of another thing about this curve, more information about this curve, is that if I look at the area of this curve, area under this curve, from the mean minus 1 standard deviation to the mean plus 1 standard deviation, this is 68% of the area. Approximately 66. Geez, am I like 66% of the area? Glad I wrote that down. Okay. 68. It's 68 because it's 34. Right? Thank you. Yeah. You know, as those of you who already know how to do this, you know why I don't remember this number real well. Because I just get the numbers out of my calculator. Okay.